Thank you, everyone. I have committed the cardinal sin of not having my slides ready to go. There we are. All right. So by trade, I am a software engineer, and I am interested in complex critical software systems. So those are systems that are so large, they have to be made over a long term by some sort of organization, and critical in the sense that they can't fail. And when they do fail, very bad things happen. So what I'm interested in particular in terms of research and learning how to build these systems effectively are techno-political artifacts. So that's a bit of technology that influences a political organization like a business or a government, and the organization influences the technology. And I'm interested in and also worried about failure in such systems. So how do failures influence the evolution of this techno-political system? And for me, in my research, in learning how to build these complex critical systems, spaceflight is a huge boon because it's also that same sort of techno-political artifact, and it's extensively well documented through time. So what I want to do in this talk is examine one aspect of spaceflight, which is space stations. And I want to take that concept of space stations from the earliest theorizing in the first part of the 20th century all the way through to implementation to the modern day. So the early 20th century is a fascinating time for rocketry. And it's a fascinating time because it's a moment in history when theory and practice are rapidly intermingling. You have people like Konstantin Tsiolkovsky, you have Robert Goddard, you have Hermann Oberth, all theorizing about rockets, working out the fundamental mathematics, the fundamental physics to make spaceflight possible. And at the same time, several of these men are working on making their theories practical realities. So in March 1926 in Auburn, Massachusetts, Robert Goddard achieves the first flight of a liquid-fueled rocket. This rocket looks kind of goofy because people weren't sure how to build them. The thrust chamber is at the top and the fuel is at the bottom. It only flew 41 feet high, and it detonated in a cabbage patch, but it was sufficient to demonstrate that it was possible to build rockets. In 1930 in Berlin, Hermann Oberth, who had written about rockets in 1923, inspired by the practical work that Robert Goddard had done, flies his first liquid-fueled rocket. And then Sergei Korolev, in 1933 in Moscow, inspired by both Robert Goddard and Hermann Oberth's work, flies his first liquid-fueled rocket. So you have people in the United States, in Germany, and in Soviet Russia, in the Soviet Union, flying rockets. And theorizing about how these rockets will work. And the one problem for these researches is that rocketry is very expensive. Not only are the materials and fuels expensive, but the fuels especially are very dangerous. And danger, if you don't want to die around dangerous things, implies cost. So Robert Goddard works to get contracts from the US Army. Hermann Oberth works with the Weimar Republic German Army to get funding for his rocketry research. And working for nation states is kind of a deal with the devil, because nation states have a lot of money, but they have very particular or peculiar ambitions for their money. So Wernher von Braun, who was Hermann Oberth's student, and was actually in that photograph of Hermann Oberth, continues to work for the German army as it turns into the Nazi army, and he gets to build a rocket facility. And this is an overflight by the RAF of Wernher von Braun's rocket facility in Peenemünde, Germany. And in this facility, he builds aggregate devices, a series of rockets, 1, 2, 3, 4. And the aggregate 4 is a very impressive rocket. It uses gyroscopic control, which Robert Goddard had proved out in the United States in 1933 to very accurately control its flight path. It's liquid fueled, it has a relatively large payload, but there's that deal with the devil thing. The world actually knows the aggregate 4 by a different name, the V2. So in the last days of the World War II, the Nazi government launched thousands of V2s in a bid to break the resolve of the Allies. The Nazi government actually invested a lot in super weapons. They kind of felt that they could develop these weapons that were so terrifying that their enemies couldn't oppose them. And they had even wackier plans than the V2. And I don't mean wacky in the sense that they're amusing. I mean wacky in the sense that they're completely unhinged from reality. And the one that fits best in this talk is actually called the space gun, or the sun gun. What it is it's a giant mirror in space that has a little control tower on the side opposite the sun. And what this mirror is meant to do is focus the rays of the sun on enemy cities and then burn them from space. So this is taking research that Herman Oberth did in theorizing about rockets. He also theorized about space stations. Tsiolkovsky did that. It's taking that research and putting it into an insane military application. And even though the rocket scientists are working with governments, the rocket scientists aren't dreaming about blowing things up with their rockets. They're dreaming about doing weather observation. They're dreaming about learning about the upper atmosphere. They're dreaming about photographing the Earth to discover things that we can't see up close. They want to be scientists. They want to explore. And the prevailing notion is if you're going to explore, you need a place to explore from. So hand in hand with the early theory of rockets is the theory of space stations, the theory of, okay, well, if I've got this rocket, then I can lift a station, and then I can keep going back and forth to that station, and I can observe things. And you have Tsiolkovsky in 1903, who writes about a rotating orbital station to produce artificial gravity so that men can do astronomical observations above the atmosphere. You have Hermann Nordung in the 1920s with The Problem of Space Travel, who describes as well another rotating station, 30 meters in diameter. And you can see that the outside it is indeed a massive laboratory. And the thing that I find most charming is to transition between sides. You can actually take the spiral path in the middle, and there's like a charming brick stairway to get to the other side. So the working notion for rocketry experts becomes, if you're going to have human exploration of space, you're going to need a space station in orbit. It's considered an essential and necessary step for sustainable exploration of space. And there are recognized problems with this. There are recognized unknowns. And in the 1950s, a series of rocket scientists write a series of articles in Collier's, the first article of which is Man Will Conquer Space Soon. And it describes a program by which the United States and the free countries of Europe can build a program to get into space in a sustainable fashion. And Wernher von Braun and Cornelius Ryan propose a thing called a baby space station. So before building a large space station, we need to understand certain things. In particular, one of the huge unknowns about spaceflight at this time is the effect of weightlessness on mammalian body. Will our hearts be able to pump blood? Will our eyes fly out of our heads? Nobody knows answers to these because the only people who have ever been weightless have been people in plummeting elevators, and they haven't really been able to tell us about the experience. So to that end, in this article, von Braun and Ryan, they detail this experimental satellite. It'll carry 3 rhesus monkeys, one of which is strapped down and has biometric probes in its body, and then the other 2 are allowed to move around so that we can study using television, which is relatively new at the time, how the rhesus monkeys adapt, and we can see how the strapped down monkey, how its body changes. And it was to be a 2-month mission. And usually when I introduce this, if I introduce it to children, they ask, well, how do you get the monkeys back? And the answer is you don't. You burn them up when you're done. Which is hard to tell the kids. Yeah. So then they go on to propose an observatory. And this should look very familiar from the early theorizing. It's meant to be this massive space station with hundreds of people, ferries going back and forth in space, space planes coming up from the Earth to deliver scientific equipment, to bring resupply. So experts in both the Soviet Union and the United States, they expect to build space stations in near-Earth orbit and then go on to explore the solar system. That lasts until 1957. So the International Geophysical Year happens, and the United States declares that it's going to launch the world's first artificial satellite to study the Earth. The Soviet Union, Sergei Korolev is ordered to beat them. And he puts together Sputnik in, I believe, less than 6 months, and then launches it. So the Soviet Union puts Sputnik into space. And this success puts pressure on the USSR to claim more firsts. So it becomes a political need to shape the space program to be first in things. And indeed, they have very good success. In 1959, Luna 3 takes a photograph of the far side of the moon. In 1961, Yuri Gagarin becomes the first human being in space. In 1965, Alexei Leonov does the first EVA, the first extravehicular activity. He goes outside of a space vehicle. In 1966, Luna 9 succeeds in making the first transmission from the surface of the moon. And in 1969, Soyuz 4 and 5 achieve the first docking of two manned crafts. In particular, what I find very interesting about Soyuz 4 and 5 is not only did they decide to dock two spacecraft with people inside of it, they decided to go ahead and switch crew at the same time, just for giggles. Sputnik puts pressure on the US to catch up with the Soviet Union. So in 1961, Alan Shepard becomes the first human being in space. He rides the Freedom 7 in a ballistic arc, goes into space, and then comes right back down. A mere 3 weeks later, John F. Kennedy addresses the United States Congress, and he says that by the end of this decade, we will land a man on the moon and return him safely. And in his proposal, at no point does he mention a space station. So he has committed the United States to a political aim of beating the Soviet Union, and in doing so has defied the common notion of what is necessary for long-duration, sustainable spaceflight. So this influences how the Americans start to plan out their lift vehicles, how they start to plan out their program of research to make the Apollo project happen. All space station research is stopped because the new aim is merely to get to the moon. In 1965, the first American EVA happens. This is Ed White. He bounces around at the end of his tether, just like Alexei Leonov did. Nobody can do effective EVA work yet, so there's no construction in space. Gemini 6 and 7 in 1965 achieved the first Rendezvous. Gemini can't dock, so there's no docking and transfer, so they station keep. They merely just sit next to one another. But Rendezvous is a very hard problem because space is weird, orbits are weird. In 1966, Gemini 8 achieves the first docking. This docking is done with the Agena Target docking vehicle, which is basically a big dumb radio transmitter that's made out of the lift vehicle that brought the Gemini up. In 1966, the first effective EVA is done. So Buzz Aldrin crawls around on the outside of his Gemini spacecraft, and he fiddles with some construction work. Buzz Aldrin also has Buzz Aldrin is also distinguished by being the second man on the moon, but he does have a very interesting first in addition to the EVA. He took the first space selfie. So Apollo 8 in 1968 is the first manned lunar orbit. So in the Soviet Union realizes that the United States is actually serious about abandoning sustainable spaceflight, that they're not going to build a space station. And they realize that politically they have to catch up. They also need to achieve a lunar landing, ideally before the United States. But they're behind. And they look at Apollo 8 and they say, oh, this is going to blow up, because the Apollo 8 looked pretty dangerous. It was only the third flight of the Saturn V. Only the third one. Usually rockets blow up a lot while you're developing them. But Apollo 8 didn't fail. And so this, combined with the unplanned decomposition of the Soviet N-1 rockets, really put a damper on the Soviet lunar project, and it would eventually be canceled. And much of the technology will show up later, because they had gotten quite far in it. And then in 1969, humanity reaches the moon. Neil Armstrong and Buzz Aldrin both stepped out, they left some scientific equipment, they got back in, and they flew back home. So the success of Project Apollo really spurs the Soviet Union and the United States to switch gears. So the Soviets focus on expanding expertise in space operations. They start to focus on that sustainable path to a future in the solar system. And the US focuses on opening up space. So NASA, coming off of Project Apollo, is really enthusiastic about laying the groundwork for a Mars mission. And this for them means solving the lift problem of developing a cheap-to-operate space vehicle to build a station in orbit, and then after they build the station, to then prove out all the techniques that you need to get to Mars. Having a cheap-to-operate lift vehicle also dovetails nicely with NASA's increasing budget problems, as the success of the Apollo project really kept slashing NASA's budget because we wanted to, in the United States, pay for the Vietnam War instead. So in 1971, Soviet Union launches Salyut 1. Salyut 1 is the world's first space station. And it's very difficult to see in this photograph, so there's a diagram of it. On the left-hand side, you'll see the Soyuz spacecraft, which is the ferry for the cosmonauts. It's a little more than a pressure chamber and then some seats. And the descent module, and then there's a larger module, which is the round bit at the front, which has the docking adapter and has more movable space. The Salyut 1 is based on the Almaz, which is the Soviet Union military reconnaissance station. So the notion was that you would launch the station and you would have people inside take photographs. The United States actually tried to develop one of these things too. It was called the Manned Orbiting Laboratory, which is it's not a good name because it was not a laboratory. It was meant for spying purposes. But because of the development of automated spy satellites, the United States never developed that. To help prove out the concept of military reconnaissance station, the Salyut 1, the civilian craft, was launched instead. And the Salyut 1 was really an experiment. So the crew were meant to prove out station systems, to prove that the water reclaimer worked, to prove that the oxygen generator worked, and study their own adaptation to space. So at this point, the Apollo project had generated the longest duration space flights, but those flights were relatively short. So the biomedical component of Salyut 1 was particularly pioneering. The Soyuz crew, manned Salyut 1 for 23 days until a fire broke out, causing them to abandon the vehicle. So because the Salyut 1 was expendable, it could not be refueled, it could not have repairs done to it. There was no point in staying inside of it if it might catch fire again. And besides, they'd already been there for 23 days and they'd already collected science to demonstrate that they hadn't fallen to pieces, so they were going to land. Unfortunately, the crew died on the way down. A valve meant to equalize pressure lower to the Earth opened up in high atmosphere, and they were exposed to vacuum because at that time, due to overconfidence, I think, in the effectiveness of the Soyuz as a vehicle, they didn't wear pressure suits. So they were just in a shirt-sleeve environment. So as we go through these space stations, I kind of want to have like an inside baseball view of the station. The most important one, I think, is the operational lifetime. How long did the space station exist? How long were we able to maintain this machine in space? And the Salyut 1 had an operational lifetime of 23 days. It was expendable. Once you ran out of consumables, that was it. You were out of oxygen. So in 1973, NASA, as a part of the Apollo applications program, launches Skylab. So after the Apollo project ended, NASA has a lot of hardware left over. And Skylab was the winning proposal for what to do with that hardware. The Skylab itself is a repurposed second stage of a Saturn V vehicle. In the place of liquid hydrogen, you have the orbital workshop. So inside of a fuel tank, they built a science laboratory. And then the oxygen tank in the Saturn V second stage was for dumping garbage. In the top, they've added a docking adapter for the command module, and then there's the Apollo telescope for studying the sun. Unfortunately, the launch of Skylab was a little off nominal. So Skylab is supposed to look like this. It's supposed to have two solar arrays on either side, two arms that come out. It's supposed to have a micrometeor shield that sort of pops up off the top of the orbital workshop and provides impact deflection, and at the same time provides passive cooling for the orbital workshop itself. Heat is a really difficult problem in space because there's nothing to wick it off. So you have to explicitly radiate it or continually be in shadow and then heat yourself. Unfortunately, during launch, the micrometeor shield popped up prematurely in the atmosphere and was ripped off. And when it was ripped off, it happened to take one of the solar array arms with it. And at the same time, to add insult to injury, it pinned down the other one with metal garbage. So rather than abandon the Skylab, because it was very expensive and they believed that they could repair it, the first Skylab mission was sent up to cut off that metal strap, and then Charles Conrad strapped himself to the outside of the Skylab where there were no EVA handles, and then he lassoed the end of the solar arm and then pulled it up, just yanked it up. And then, because they need a shield from the sun, what they did is they got a bunch of tent material and they attached it to expanding arms, and they poked that tent material through one of the scientific airlocks. telescoping out over the workshop. So you get this curious little tent thing that pokes out of the Skylab. This is a hugely impressive ad hoc repair mission. Otherwise this multi-billion-dollar space station would have been left to rot. It would have just simply burned up. And once repaired, the Skylab was a very effective laboratory. So this is scientist astronaut Garrett at the Apollo telescope mount. So before Skylab, humanity had never been able to look at the sun in a scientific fashion not mediated by the atmosphere. But with Skylab, we were able for the first time to study the sun, to start to understand the sun's processes, to capture solar corona emissions in real time. The Skylab also did Earth observation. So to figure out how crops were growing, to try and find faults that we didn't realize existed. And this is Chicago. I think Chicago looks really nice, both up close and from space. Skylab also grew crystals. So one hope for manufacturing in space is the production of crystals for industrial purposes that have a very pure structure, because in microgravity, crystals, we have found out through experimentation, grow in a much different way than they do closer to the Earth. Biomedical experiments on spiders were done as kind of a get children interested in space again. This particular spider is named Arabella, and it took her 3 weeks to learn how to weave her webs. The astronauts kind of griped that the spiders were more popular than they were. The main thing that we learned through Skylab is what happens to the human body during long-duration space flight. So the astronauts were themselves guinea pigs. This is Alan Bean, and he's on the ergometer, which is basically a space bicycle. And he's doing the metabolic activity experiment. So what NASA doctors are trying to learn is, as we're in microgravity environments, does our ability to digest change? How are we able to arrest bone loss? Because it would be a real shame if we, in a big hurry, launched off to Mars and then found that we starved to death halfway there because we weren't able to effectively adjust the diet for needs in a microgravity environment. And Skylab made a huge advance over the Salyut. It was much larger. It was also not resupplyable. It was also not extendable. It was monolithic, but it was larger because it was built out of a rocket body. So it made it to 171 days. And then as we go through, because it's kind of hard to keep numbers in mind, I kind of want to compare graphically as well. So you can see how much further Skylab was able to go. Unfortunately, Skylab was a one-off. There was no repeating Skylab. In December 1974, Salyut 4 was launched. And I've skipped from Salyut 1 to Salyut 4 because Salyut 2 and 3 were the military variant of the Salyut body. They were actually called Almaz, but the Soviet Union, being very secretive, would launch these things and just call them extra Soyuz. Or Salyuts, excuse me. It was easy to tell that they weren't civilian vehicles because they used military transmission frequencies, but I don't know much about them because they're still kind of secretive, so we're just going to skip them. So whenever we skip numbers, there's just military stuff in between there. So Salyut 4 is meant to prove out the design's long-term durability. Is it possible for us to sustain these machines in space? And two Soyuz missions, Soyuz 17 and 18, performed solar and biological experiments. How do our bodies adapt? What does the sun look like? But Soyuz 18 in particular did much to advance Soviet microgravity medical knowledge through experimentation of devices on the cosmonauts. One was called the penguin suit. So one problem with being in space is that our muscles atrophy because we're not using them. So the penguin suit goes around the bottom of your foot and it provides continued active resistance to your feet because it's basically a spring and it makes you look a little bit like a penguin. The other one is the Chibis suit. This is basically the opposite of a G suit. So instead of pushing fluids away from your legs, it pushes fluids toward your legs because in microgravity, it turns out that fluids pool in our upper torso and head. And the Chibis suit is meant to suck all of that back down to help you readjust to living in 1G. And by the end of Soyuz 18, a rich green mold was growing throughout the station because the environmental system broke down. It wasn't repairable. And it was clear that stations were going to have to be repairable if they were going to be suitable for long-term habitation. Because every crew that comes up brings funguses, they bring bacteria, they bring microbes, and you need equipment to filter that out. You need cleaning equipment. And that all has to be replaced and repaired. Apparently the Soyuz 18 crew was very relieved to have their mission terminated early. And the Soyuz 4, as befits a long-term mission, was a significant advancement over Salyut 1 and made it to a full 92 days. And I keep skipping over that. And you can kind of see that visually, that it is a significant advancement in the Soviet program. Salyut 6 was launched in September of 1977. And Salyut 6 is a revolution because it can be resupplied. So all the stations before were what are called monolithic. They're not resupplyable. And it achieves this by having an extra little feature. So this is the Salyut here in the middle. This is the station. This is the Soyuz, which is the ferry vehicle. And then on the end, you have the Progress. The Progress is a Soyuz variant that has all of the environmental systems stripped out, and it's cargo instead. And what it's doing is it's docking with a new aft port on the back of the Soyuz, or in the Salyut, so that the cosmonauts can unload this thing. The Progress and the Salyut also have the interesting capability of using pipes built into the docking clamps to channel fuel and oxygen into tanks that exist on the station. So the station can be continually replenished while major systems last. The only limitation here is that the Progress is kind of small. So if you have a particularly large system that needs to be replaced, say a solar panel, you don't have much capability to do that. So resupply dramatically increases the lifetime of a station, and increased lifetime decreases total cost, so you can get more science out of a thing that's already in orbit than having to continually relaunch something every 40 days. Increased lifetimes also teach the Soviet program how to coordinate and train for ad hoc repairs. So if you have this thing that's important, you have to learn culturally how to care for it. You can't just abandon it because there was a small fire. You have to deal with that fire. And on the Salyut 6, the Orlan is first tested. So the Orlan is from the canceled Lunar project. It was meant to be the lunar excursion suit. But the Soviets realized that if they're going to have these long-duration space flights in terms of space stations, they have to be able to get out and crawl around. And the Orlan was tested in 1977. The last Soviet spacewalk had been in 1969. So there's been an entire class of cosmonauts that have never done a spacewalk. And the Salyut 6 lasted for 683 days. So it really, really was a revolution, even over Skylab, which was much, much larger. The ability to resupply is a significant advancement in this particular technology. In April of 1981, STS-1 is launched. So the Americans have been trying to solve the lift problem, and this is the first flight of the Space Shuttle. While the Soviets have been building these monolithic stations and launching them, the US has been building a pickup truck to the stars, and NASA promises, because they've entered their hard boondoggle era, that the Space Shuttle will be able to launch once a month, and they'll be able to resurface satellites. And this is a cutaway of the Space Shuttle. The Space Shuttle was a hugely complicated machine, but what I really want to point out is just how much the cargo bay of the Space Shuttle dominates the vehicle. It is a vehicle that's designed to move things. And the ambition for the shuttle, in what NASA went hat in hand to Congress to get funding for, the ambition for the shuttle is to cheaply launch and service sensitive satellites. So the shuttle actually flew quite a number of Department of Defense missions, as well as do microgravity research. So here, for instance, is a photo of a shuttle mission where the shuttle captured satellites that were already in orbit that simply needed refurbishing to be effective satellites, and then to be relaunched, refueling, things like that. And the shuttle in its early days did a number of missions like this. Coincidentally, the shuttle is ideally suited to assembling and servicing large-scale space stations. So NASA still has its eye on the prize. It still wants to get to Mars. It doesn't know when, and it doesn't really care how, but it knows that it needs this capability. Unfortunately, the shuttle is limited to 2-week missions, which denies NASA operational experience in long-duration spaceflight. So because shuttle missions are so short, every minute is time-lined out. You do these things, and because the missions are so short, if there's a mechanical problem that occurs, you just abandon the mission and you fly back home. So NASA becomes this organization that becomes incapable of having lax schedules, of having downtime, of having just goals for a day and letting your astronauts work through those goals. April 1982, Salyut 7 is launched. So Salyut 7 was nearly identical to Salyut 6. Salyut 7 was intended to be the backup for 6, but with Mir's launch continually being delayed, they did not want to lose their edge. They wanted to keep having a station in orbit, so they went ahead and launched the backup. And they reinforced certain segments of the station to give better experience in modular construction for the Mir. And Salyut 7, on account of growing confidence, is a lot more crowded than Salyut 6, both with more expensive scientific equipment and both in terms of people. So the Salyuts would have a nominal crew of 3, and then you could have guest cosmonauts. And because of the way the environmental system was designed, if you had guest cosmonauts, you had to burn what people referred to as an oxygen candle, which is a device where when you heat it up, it consumes, the consumable in it produces oxygen as it burns. So they would have to put these things in, and they would have to have extra carbon scrubbers because the station is really not designed for this. So a series of breakdowns actually makes Salyut 7 much more interesting in the history of space construction. So on September 9th, 1983, a pipe in Salyut's unpressurized engine bay fractured. So if you'll recall, Salyut 6 was able to accept resupply. Salyut 7 had that same capability because it was identical, but one of the pipes broke. And because Salyut 7 was still relatively young, it was decided to try and repair it. So on April 23, 1984, cosmonauts Kisman and Soyuz begin a series of 5 EVAs to repair the leak. So to repair this leak, which was called a coffin problem in the planning material, it was felt that this was not a repairable thing. What they have to do is they have to open up an outer bulkhead during an EVA. They then have to go cutting through pipes. They have to replace a bunch of valves. And all of this work is non-trivial on the Earth. And they're doing this in space where your tools float off, where you have sausage fingers because your gloves are relatively massive. So it's a very difficult job. And you can see that, you know, April 23rd, 26th, 29th, May 3rd, August 8th, it takes them a long time to achieve this aim. And it's also worth noting that the Orlan suit limited them. Each one of these EVAs is less than 6 hours. And the reason it's less than 6 hours is because at the 6-hour mark, you run out of primary life support inside of your suit. And you don't want to run out of primary life support. So on February 11th, 1985, power was lost aboard the Salyut 7, and it began to free drift. So the ambition for the Soviet program was to have continuous occupation. But because of logistics problems, because of delays, they didn't quite meet that ambition in the Salyut 7, and so the leaving crew mothballed it, put it into a low power state to be picked up by the next crew. Unfortunately, because it free drifted, it had to be decided, do we fix this or not? And the Soviet Union decided, yes, we will fix this. And Soyuz T-13 was dispatched to repair the station. Now, the Soyuz, the Soviet program is invested in a lot of automation, and the Soyuz is meant to automatically dock with its space station. But the station is dead, so they have to use laser rangefinders to guess intercept trajectories to dock with this dead station that is tumbling in space. They manage to do it, but when they get inside, the temperature is negative 10 degrees Celsius. All the water pipes had frozen, you know, huge mess inside. So the cosmonauts had to wear fur hats, fur coats, fur boots, and when they would get too cold, they would have to go back into the Soyuz and warm up, and that's where they would have to sleep. But eventually, they found out what the problem was. There was a switching mechanism that would switch to the batteries that needed to be charged. As the solar panels fill up a battery, it would then switch over. The switching mechanism failed, and ironically, the Salyut 7 died because it drained its batteries, turning its solar panels to charge its batteries that it wasn't able to keep charging. If the station had had continuous occupation, this would not have happened, because a cosmonaut would have noticed, there would have been a little alarm going off, and it would have been a very short operation to replace this thing. So this really underscores that space stations have to be continuously occupied, because in space, any minor issue that's left untreated becomes a major crisis, because space is a very harsh place. But once repaired, the Salyut 7 hosted another 3 missions, as well as a flight from Mir to Salyut 7 and then back again, which is the only time humanity has ever flown from one space station to another and then back again. And what they were doing was they were taking expensive scientific equipment out of Salyut 7 to use on Mir. Previously, all of that expensive scientific equipment would burn up in the atmosphere when the station deorbited. And Salyut 7, being basically identical to Salyut 6, operated for 816 days, so roughly the same as Salyut 6. It was not an advancement to the art, but it was an advancement in the state-of-the-art of logistics, in repairing craft in orbit. In February 1986, the Mir base block is launched. And Mir is the first modular space station, and it's intended to be continuously occupied. So they've learned the lessons from Salyut 7. And Mir is basically a Salyut with a docking node instead of just a Mir front docking port. In March 1987, Cavant 1 is launched. And Cavant is 2 working compartments and an unpressurized experiment compartment. And it goes in the aft docking port. And you can kind of see it off to the right up to the top. The thing with the solar panels on the outside is the Soyuz, so that's the ferry craft. In November 1989, Cavant 2, which provides an EVA for airlocks. It provides a cargo bay, which can also be used as a backup for EVAs. And it provides another experiment compartment. In 1990, in May, Crystal, which is a furnace compartment for growing crystals, an astronomical observation compartment, and most importantly, a docking module for Buran. Buran was the Soviet Union's Space Shuttle variant, which did fly once in automated control. Unfortunately for Mir, on December 25th, 1991, the Soviet Union completely collapsed. So there was no money for anything anymore. All of the plans for launch had to be scrubbed. In June 1992, Presidents Bush and Yeltsin agreed to cooperation in spaceflight. So Yeltsin agrees to fly cosmonauts on the Space Shuttle, and Bush agrees to fly astronauts to Mir, partially constructed as it is. In September 1993, the Clinton administration has come into power, and the US Vice President and the Russian Prime Minister, not only do they keep Bush's proposal or plan, but they add to it by agreeing to jointly build a space station in orbit. So the United States, since the Reagan administration, has been wanting to build what's called the Space Station Freedom. Bit on the nose, Reagan. But what they agree to instead is to have international cooperation in constructing and maintaining an orbital facility. And it's to be the International Space Station. The construction of the ISS will occur in 3 phases. Phase 1 is the Shuttle Mir project. So the shuttle will help complete the Mir and ferry equipment back and forth to the Mir. Replacement supplies, scientific equipment. Phase 2 is the construction of the International Space Station itself. And Phase 3, which is the phase we're living in right now, is the operation of the International Space Station. Phase 1 is vitally important for both partners. The Russian space station program, or the Russian space program, is running out of money. With the collapse of the Soviet Union, now it has to exist in a market economy where a market economy did not previously exist. And the US space program has not had long-duration space flights since Skylab 4 in 1974. So it's completely lost the organizational capability of dealing with something like that. So in May 1995, Spectre is launched. Spectre is to be the place where US astronauts live and where they do their experiments. Most notably, Spectre has 4 solar arrays, so it provides 1/2 of the power of the Mir space station. In November of 1995, the docking module, which is an adapter for the space shuttle. Previously, if the shuttle was to dock, the Crystal module would have to be moved because the space shuttle would bump into solar panels and destroy them. And then in April of 1996, Prioria is launched, which hosts Earth resources experiments, and it's to help prove out techniques to be used on the International Space Station. So Mir, it's a significant advancement over the state-of-the-art in that Salyut 7 was a one-shot deal. Once you were done with it, you could not extend onto it. Mir, however, theoretically can continually be operated, continually replaced. It's a modular space station, and it's hugely complex for the time. Unfortunately, by the time of the shuttle Mir, several of Mir's modules were nearing the ends of their lifetimes. The collapse of the Soviet Union had put a real damper on the project timeline. Cavant 1 was described as dank by more than one astronaut. The environmental system down there failed pretty badly, so it was mostly used to collect trash. Balls of water formed regularly behind wall panels and had to be mopped up. Those balls of water would then breed fungus and mold. But even despite those problems, Mir was a very human place and had well advanced the state of the art. Significant amounts of science were done, both on the cosmonauts and the astronauts, and in Earth observation, in solar observation, in observation of comets. Famously, though, Mir suffered 2 near-catastrophic system accidents during the Shuttle Mir project. The first occurred in January 1997. One of those oxygen candles that I talked about earlier, instead of gradually burning and producing oxygen, produced a blowtorch instead and severely burned the module that it was in and polluted the station's atmosphere. And it took 9 minutes to put that fire out. The worst one occurred in June of 1997 when an experimental docking technique was attempted with a Progress craft, one of these multi-ton vessels, and it slammed into the Spectre module, significantly damaging the solar panel, but even worse, puncturing the Spectre's hull. So the station started to leak atmosphere, so they had to abandon the Spectre. The trouble with this is that the Spectre produced 1/2 of the station's power, so they had to figure out a way to reroute power, and that was a significant repair effort. And because of these problems and because of the upcoming International Space Station, the Mir was finally abandoned after 4,592 days, which is a significant advancement over any of the previous space stations. In November of 1998, the International Space Station base block is launched. And the base block called Zarya is Mir's base block. So at the core of the International Space Station, after the close of the Cold War, the core of the International Space Station is Mir. The second module connected to the International Space Station in 1998 is Unity. Unity is a connecting module. It just has docking berths. Zveta comes in 2000, and it provides station life support, and it houses 2 crew. Sveta is a Salyut space station. So the core of the International Space Station is Mir and Salyut. In 2000, the Z1 truss comes, and this is a place to connect up equipment. In 2000, again, you get the P6 truss and the solar arrays. So the space station draws a huge amount of power. And to give you a sense of scale of the space station, these are 2 astronauts doing an EVA to finish the installation of one of the trusses. And they're diminutive next to the space station. In 2001, Destiny is launched. Destiny is the first US laboratory in space since Skylab. And this is the inside of Destiny when it was unpacked, when it was just installed in 2001. And this is the inside of Destiny 5 years later, with all of its equipment unpacked. Canadarm comes in 2001. Canadarm is an update of the shuttle's arm, so it's a crane for manipulating things. And the cool thing about Canadarm is that it can crawl around the outside of the space station. It can move itself by inchworming along. Canadarm can be used to help move astronauts to hard-to-reach places. It can also grab what's called Dexter, and Dexter is a dexterous manipulating tool for repairing components or moving components around. I don't want to go, we don't have time to go through all of the modules of the space station, but I just kind of want to go through its construction to give you a sense of what an immense effort it was to produce this thing. The European Space Agency, the Russian Federation, NASA, the Japanese Space Agency, made this gigantic orbital lab. And it's not even finished yet. All these pink modules have yet to launch. The ISS is absolutely massive. The cranes, effectors, and crew transports set it apart as being uniquely adaptable. And it's a human object that's meant to be tinkered with. It is meant to fundamentally advance humanity's knowledge of living and working in space over the long term. And you can see that the initial concepts of what a space station should be, a rotating device that had hundreds of people on it, turned out not to be true in practice. And one of the things that I'm most interested in one of the experiments that I'm most interested in the space station is the BEAM, which stands for the Bigelow Expandable Activity Module. So 2 problems with building in space are the lift weight of a thing and the lift size of a thing. And the BEAM is meant to prove out the concept of launching something that has a fixed weight but is able to expand its size. And this was actually launched this year in April 2016. And the ISS is a significant advancement over the state of the art in Mir. It really learned from Mir's problem, and it's been operating for 5,823 plus days. And what really strikes me is 385 plus people have been aboard the International Space Station. And it's still going, and it's meant to continue to go into the 2020s. Unfortunately, for a thing that's called the International Space Station, the US Congress actually has excluded people from participating in the project. Countries. One such country is China. So the Tiangong-1 launches in 2011, and it's meant to help China prove out space station technology so that it can build its own large space station. And it's little more than a Salyut, like an early Salyut. It's not refuelable, it's not expandable, and they do biomedical experiments on themselves. And they have a limited lifetime, 26 days. It's said to be 30 days in total. Tiangong-2 went up in September of 2016, and they're still up there. If you look at Chinese TV, they will broadcast segments of what the astronauts are doing. They ride up in basically a Soyuz, they dock like a Soyuz, and they live as if they were living in a Salyut. And that's 15 plus days. And so the timeline of these space stations, there's quite a bit of overlap as the nation states sort of learn how to build them and how to keep them going. And the question I get asked when I talk about space stations is why? You know, why not have a lunar base? Why not just go straight to Mars like we did with the moon? And the answers are space stations are a safe environment to do long-term biomedical research. You're never more than a few hours away from being home if something goes drastically wrong. Space stations are a safe environment to learn the logistics of long-duration spaceflight. So say your oxygen generator dies and then your backup dies. Well, then you just launch another one up. You can't do that if you're on the way to Mars. It's more expensive to do that if you're on the surface of the moon. Space stations give us a platform to study the psychology of high-pressure isolation. So being in a small crew in a tin can for months at a time, what does that do to a mind? The United States learned in the Shuttle Mir project that several of its shuttle astronauts were not suitable for space station work. Space stations influence lift vehicles, so they provide a broad context for problem solving. So when you start to imagine, what should I build, you have this notion of sustainable habitability in space when you're designing vehicles. And underlying this, there's a broader answer. And that answer is because Mars is there. You know, since the start of the 20th century, when people first realized that we could escape the Earth's gravity well, we've wanted to go to Mars. And to my mind, to reach Mars will require the work of our better natures. You know, the work of nations in cooperation, not in opposition and war. You know, President Kennedy, when he was talking about the moon project, you know, when he said that we would go to the moon, he said that, you know, new hopes for knowledge and peace are there. And I fully believe that if we actually do all the work, if we learn how to harness complex techno-political systems to reach Mars, then we will have found new knowledge and peace.